Hello everyone. So this presentation today is about the moon phase rotation when it's being filmed from moonrise to moonset and how it moves in different directions and different rates. And I'm going to show that this proves that we live on a spinning ball that goes around the sun. This presentation, it could be concluded in just a half-a-minute video showing the simulation that I made based on some like 5 elements of the heliocentric model. But if I do that, you wouldn't appreciate the beauty of our world and the elements that I'm going to work with. So I need to take your hand through additional 2 segments that I have to start with, just to show you the basics to how I do these calculations and maybe inspire some other to do things like that. So the first segment, I call it the flat and stationary, and that term is being used sometimes by some flat earthers, claiming that the heliocentric model astronomy is based on a flat and stationary Earth. No, that's not the case. It's just misconception and probably a poor term on the side of the mainstream science. So I'm going to show you now. This is a flat patch of land. This is like it's covering my whole city, Cairo, here. And so this patch of land, it could be any size as long as it's flat. It can even the size of your palm. Now you see this is here in Egypt, this patch of land, and I'll be looking from the west side towards east. I'm sorry for this being a little bit slow. I even did it in video to expedite the process. So now I'm going down because I want to look side view into that patch of land. So we have a flat patch of land, and then I look upward to show you as much stars as I can. And it's going to be a little bit funny because this is a 120 degrees field of view, just to get as much stars as possible. And what happens when I start moving the clock? When the clock moves, notice this group of star. It's going down in an angle. So this is the movements of the star with this direction. That's because I'm on latitude 30. But anyway, when we started the clock, it's allowing the globe to rotate, but this flat patch of land, it didn't go anywhere because the observer, which is me, I'm looking towards it and I'm standing on the same planet. So the stars moved relative to us. You can say it this way. So now I move to the second part, but hold on to this idea of this flat patch of land because we're going to use it heavily next. Not this one. Yeah. So what you see here, this is not the Earth. This is what's called the celestial sphere. The Earth is a tiny dot in the middle. The celestial sphere is, imagine the stars are like lights that are painted on the interior of a black sphere, and we are just in the center. So because of Earth rotation, we see that this whole celestial sphere is the one that's rotating in opposite direction to our direction. So this star here, it will be moving in that direction, and we are in the center observing it. Now this star here, if it was in the equator, that means it would be having a declination of 0 because the angle between it and the equatorial plane is 0, but for this one, this is like maybe 30 degrees declination. So when the star moves, and if you take the line of sight from the Earth towards the star, yes, this one, then after 24 hours, that line of sight will sweep, making a cone. We're in the center of that cone. Now that cone's size is enormous, but we don't care about size, we care about the ratios. And the ratios are defined through this angle, which is called the declination angle. So now we go to back to our flat, stationary patch of land. We scale down the cone of the star. And when you look from here, you see that the star rises from this point and then sets at this point. And it's obvious here that this angle is more than 180 degrees because the star is at high declination. Just like in the summer, we have longer day, and these longer days are even more longer if you are on a higher latitude. So this patch of land is maybe around the latitude 45. Now let's play a little bit with the declination angle of that star before we proceed by lowering the star towards the equatorial plane. Now you can see the more I pull it down until I don't know if you can see it or not, but it's now 0. Sorry. Yeah. So you see it's almost 0. That's why you get 180 degrees from sunrise, so from star rise to star set, which is 12 hours. And if we even pull it more down, sorry, not this one. Not this one either. I'm sorry. Okay, let's start over. Okay, I'm pulling it down. Now you can see for lower declination for the northern hemisphere, you get a shorter time for the rise and set of a star or even the sun. So the example, this is the second segment now. I'm going to take you step by step on how to calculate the star rise azimuth or the sunrise azimuth. And you can see here I revealed something when I pulled this thing down. This is the azimuth of the star rise. Now let's put it up. Back again. Oh, not this one. This one. So how do we calculate this star rise angle? Go here, and believe me, it's not complicated. It's just 3 simple trigonometry steps. And you don't have to know trigonometry, but you can know when someone is manipulating it. So here is the cone. A part of it is hidden under this patch of land. Now we'll start to extract some triangles. Right. And we'll move this background for things to be easier. Now this is the star declination angle, which is also this one. And this line here is this one, this white line, right? So if we have the length of this one, and we already have the length of this black line, you just presume any length you like. Call it 10, 1, or 100. I like to use 100. So if this is 100, through ratios I'm going to get the length of this white line. So I'll be having a triangle that I know one angle is 90 degrees and I have the hypotenuse and one side, so I can conclude the azimuth of the star rise. Now I get back here, I remove this background. So this is the 100 that I presumed, and this is the star declination angle. So and this is the right angle here, so I can get this blue line. This blue line here, let me type it fast, will equal 100 multiply the relation between this one and this one for this angle is a sine of the declination angle. So we got this one. Now we have also this angle, which is the latitude line of your location on the spherical Earth. So when we have this blue line, we can conclude the black line. This black line here is their white. I'm sorry about the bad color coding. So this one is, sorry, this one is in a cosine relation of this one. This is the hypotenuse, so it would equal the blue. I call it the blue. The blue line divide cosine the latitude. That's it. Once I get this one, I'll use the inverse cosine in a spreadsheet. Let me get the spreadsheet. The spreadsheet, and you can see the length that I presumed. Let me show you the picture again. The length, then the blue line, and then the black line. So this is the blue line and this is the black line, and the way I get them, I need to put the latitude, so I put 45 and I put 23.44. That's the sun declination angle during the summer solstice. And you can see at the end the angle is 55.76. So let's go to SunCalc and confirm that. The 20 June on sunrise, the azimuth is 54, around 54.5. I'm off by about a degree, but notice here he has the altitude of the sun minus 0.34 degrees. He's factoring refraction. This is something that must be done. You add like half a degree refraction and a little bit for the sun diameter or sun radius. So let's put in another coordinates, let's say 50. And here on latitude, let's put 50. We go to sunrise, 50.23, 51.76. Now if you started adding here a little bit of time until the sun is above the horizon, you see, or just on the horizon, you see the angle is very much similar to mine, even though I didn't account for refraction. So this is the way I do things, and this is how I work with astronomy, based on my own exploring. I didn't study any astronomy class or anything. So this is part 1, and part 2 will be the final thing, showing the simulation and more explanation.